Hello everybody, welcome back to the lectures for material and energy balances. Today we will continue with the fundamentals associated with reactions when we perform energy balances. In the last lecture we looked at what heat of reaction was. So, we looked at how enthalpy change happens when there is a reactive process. Today we will start off with something called the internal energy of reaction. So, when there is change in enthalpy, there can also be change in internal energy. So, this change in internal energy would also have to be calculated and has to be used in energy balance calculations for closed systems in constant volume. So, for this reason we need to know how we can calculate the internal energy of a reaction. So, this is defined as the difference between the internal energy of the products and the reactants if stoichiometric quantities of the reactants react completely at a given temperature and pressure. So, this would be the definition for internal energy of reaction. If nu I is the stoichiometric coefficient of the ith gaseous reactant or product and ideal gas behavior can be assumed, specific volume of the liquid and solid reactants and products are negligible, then the internal energy of the reaction can be written as delta UR cap is equal to delta HR cap minus RT times the sigma of the stoichiometric coefficients of gaseous products minus the summation of the stoichiometric coefficients of gaseous reactants. So, this is how you would calculate the internal energy change associated with a reaction. So, please note that this is valid because we are assuming ideal gas behavior for all the gaseous components in the reaction, and because the change in specific volume is very small for solids and liquids, we can ignore that, and therefore we get this equation. Here is a simple example problem which can be used to understand how to calculate the change in internal energy for a reaction based on the heat of reaction given. The standard heat of reaction for C2H4 gas reacting with 2Cl2 gas forming C2HCl3 plus H2 gas plus HCl gas is given as delta HR equals minus 420.8 kilojoules per mole. You are asked to calculate the delta UR cap for this reaction. How would we go about doing this calculation? Based on the equation we had, delta UR cap would be equal to delta HR cap minus RT times sigma of gaseous products stoichiometric coefficients minus the sigma of gaseous reactants stoichiometric coefficients. So, here let us identify what are the gaseous products and reactants. You have C2H4, Cl2, H2 and HCl all as gases. Here C2HCl3 is in liquid phase. So, we do not have to worry about this particular component. So, let us identify the stoichiometric coefficients of the reactants and the product gases. So, the product gases are hydrogen and hydrochloride. So, these have stoichiometric coefficients of 1. So, the summation of these stoichiometric coefficients is 2. Similarly, you have the stoichiometric coefficients of 1 and 2 for the reactant gases. So, the summation is 3. So, the equation then becomes delta HR cap minus RT times 2 minus 3. So, this becomes delta HR plus RT, and we have the HR value as minus 420.8 plus R is 8.314 times 10 power minus 3 because we want it in kilojoules per mole Kelvin times your temperature. So, the temperature for standard heat of reaction would be at 298 Kelvin. So, using this we can calculate the change in internal energy for this reaction, the standard internal energy for this reaction as minus 418.3 kilojoules per mole. So, this is how you would calculate the change in internal energy for a reaction, and this value delta UR cap would have to be used for reactive processes happening in closed systems at constant volume. So, moving on to the next concept, how do we actually measure this HR cap. So, we have been using the specific enthalpy value which is available from the tables, but how is this usually measured? So, heat of reaction can be measured using a calorimeter, which is a closed reactor which is immersed in a fluid contained in a well insulated vessel. So, you have a reactor which is surrounded by a fluid, and this fluid is covered by a well insulated system, so that all the heat which is generated or lost during the reaction is transferred to the liquid or the fluid around it, and nothing is lost to the surroundings outside of the fluid. The rise or the fall of fluid temperature can be measured using a simple thermometer, and this can be used to determine the energy released or absorbed by the reaction using simple energy balance calculations. So, the value of delta HR cap can be calculated and for the known reactant and product heat capacities, assuming that we have the reaction going to completion. So, what are the limitations of this technique? So, I said that this is the experimental technique commonly used. So, what could be the problem with this? If you have to determine the reaction of this equation, which is carbon plus half of oxygen forming carbon monoxide, it would be near impossible to perform this reaction without having any side reactions because you will never be able to get 1 mole of carbon to react only with half a mole of oxygen to produce 1 mole of carbon monoxide. There will always be carbon dioxide formed if the temperature is increased. If temperature is very low, the reaction rate will be too low, and we would not be able to measure any change in temperature that can be used for measuring the heat of reaction. How do we overcome this limitation? What you can do is you can carry out the following reactions and determine the heat of reactions experimentally. The first reaction which you can carry out is carbon plus oxygen forming carbon dioxide. So, this is just a simple combustion reaction of carbon, and as long as the reaction is complete combustion happens, this reaction can be easily accomplished. The other reaction is you take carbon monoxide and let it react with oxygen to form carbon dioxide. So, again this reaction is also quite possible, because once we have carbon monoxide, we can easily let it react with oxygen to form carbon dioxide, and the heat of reaction for these two things can be measured. So, once we have this, we can build a process path for the reaction of interest. So, our reaction of interest is carbon plus half oxygen gives carbon monoxide. So, this would mean the reaction which we have, which is the reaction of interest, is basically the first step where carbon plus oxygen forms carbon dioxide, and from carbon dioxide you have carbon monoxide being formed with half of oxygen. So, this is the first step is reaction 1, and the second step is the reverse of this first reaction. So, using this we can actually calculate the heat of reaction for the desired reaction. So, we know that specific enthalpy is a state function. Using this parameter, we can calculate the heat of reaction for the third reaction, which is the reaction of interest, as heat of reaction for the first reaction minus the heat of reaction for the second reaction, thereby calculating delta HR3 cap as minus 110.52 kilojoules per mole. So, this is doable, and this is what people try to do when they calculate enthalpies and enthalpy changes for reactions that cannot be carried out directly. So, this is basically calculated, the desired heat of reaction has been calculated from two measurable heats of reactions. If chemical reactions 1 and 2 are technically treated like algebraic equations, all you did was subtract reaction 2 from reaction 1 to result in reaction 3. So, that is what we have also done to the heat of reactions. So, basically we have subtracted the second heat of reaction from the first heat of reaction to get the heat of reaction for the third reaction. You can verify this with using the equations that we have. So, equations we had were the first reaction was carbon plus oxygen forms carbon dioxide, and the second reaction was carbon monoxide plus half oxygen forms carbon dioxide, and our equation of the desired equation was carbon plus half oxygen gives carbon monoxide. How do we get this? So, if we were to subtract reaction 1 and reaction 2, 1 minus 2 would basically be C plus O2 plus CO2 gives CO2 plus CO plus half O2. So, CO2 gets cancelled and this half O2 will be subtracted from here, giving you C plus half O2 gives CO2 CO. So, this is the reaction of interest and we can do this. What we did now is called as Hess's law. Hess's law is stated as if a stoichiometric equation for reaction 1 can be obtained by algebraic operations, which could be multiplication by constants, addition and subtraction on stoichiometric equations for reactions 2, 3, 4 and so on, then the heat of reaction for reaction 1 can be obtained by performing the same operations on the heats of reactions for reactions 2, 3, 4 and so on. So, this is the statement for Hess's law and this is what we just did, and we can use this to calculate the heat of reaction for reactions that cannot be performed experimentally. So, here is an example problem where we will try to use Hess's law and obtain the heat of reaction for a reaction which would not happen if you try to perform it experimentally. So, the example states that standard heat of reaction of the following combustion reactions have been determined experimentally. C2H6 plus 3.5 O2 gives 2 CO2 plus 2 H2O, C plus O2 gives CO2, H2 plus half O2 gives H2O. So, all these are given. Now, we need to calculate the heat of reaction for 2C plus 3H2 gives C2H6, which is the fourth reaction. So, this reaction would not happen in real life. Carbon and hydrogen directly reacting to form a hydrocarbon is not going to happen. So, however, the other reactions are all simple combustion reactions which could easily be carried out in a bomb calorimeter and you can measure the heat of reactions. So, that is what has been done. Now, our goal is to calculate the heat of reaction for the fourth reaction. How do we go about doing this? Let us look at the equations we had. The first equation we had was C2H6 plus 3.5 O2 gives 2 CO2 plus 3 H2O, and the second equation is C plus O2 gives CO2, and the third equation is H2 plus 0.5 O2 gives H2O. So, let us call this equation 1, 2 and 3. From here we have to get the fourth equation, and the fourth equation is 2C plus 3H2 gives C2H6. So, from looking at the equations, what we can see is C2H6, which is a reactant in the reaction 1, is a product in reaction 4. So, this means this has to be multiplied by -1, so that the reverse of the equation can be used. And now, what about the reactions 2 and 3? So, in the reactions 2 you have 1 mole of carbon reacting, whereas in your reaction 4 you have 2 moles of carbon reacting. So, you can multiply reaction 2 with 2 to get 2 moles of carbon reacting on the in the fourth reaction. Similarly, for the third reaction you can multiply the reaction by 3, so that 3 moles of hydrogen reacts. So, let us do that. So, if I were to do this particular algebraic operation, which is reaction 2 times 2 plus reaction 3 times 3 minus reaction 1, I would get reaction 4. So, let us see how that would look. So, what you have would be, when I do this operation, 2 times 2 would basically look like 2C plus 2O2 gives 2CO2, and 3 times 3 would basically look like 3H2 plus 1.5 O2 gives 3H2O. Now, reaction 1 I want to subtract it. So, this would be changed. So, the reactants become the products and the products become the reactants. So, it becomes 2CO2 plus 3H2O gives C2H6 plus 3.5 O2. So, when I add all these, what happens is these 3.5 oxygen molecules get cancelled and 2 moles of carbon dioxide gets cancelled and 3 moles of water gets cancelled, and I end up with 2C plus 3H2 gives C2H6, which is the reaction 4. So, now that I have this equation, I know what algebraic operation has to be performed to the reactions 1, 2 and 3 to get the fourth reaction. So, I would be able to perform the same operations on the heat of reaction to get the heat of reaction for the fourth reaction. So, the heat of reaction for the fourth reaction, standard heat of reaction for the fourth reaction would be equal to 2 delta HR2 plus 3 delta HR cap of reaction 3 minus delta HR1. So, this would be 2 times minus 393.5 plus 3 times minus 285.8 minus of minus 1559.8. So, this is equal to minus 84.6 kilojoules per mole. So, this would be the heat of reaction for the fourth reaction. Using Hess's law, we have been able to calculate the heat of reaction for the fourth reaction using the 3 heats of reactions which we had. All we had to identify was what algebraic operations had to be performed to actually get the fourth reaction from the first 3 reactions that were given, and then we performed the same algebraic operations on the heats of reactions as well. So, now that we have an understanding of this, let us move on to certain specific types of heats of reactions which can be used while we perform energy balance calculations. The first such reaction is a formation reaction. So, the heat associated with the formation reaction is called as the heat of formation. So, what is a formation reaction? A compound being formed from its elemental constituents as they occur in nature is called as a formation reaction. So, the enthalpy change which is associated with such a formation reaction, where 1 mole of a compound is formed at a reference temperature and pressure which is usually 25 degrees Celsius and 1 atmosphere, is called as the standard heat of formation, or it is given as delta HF cap, and this value can be obtained from textbooks and handbooks. So, if this is the case, then what would be the heat of formation, standard heat of formation for oxygen? It would be 0, because oxygen is an element in its native state. Oxygen gas would not have any heat of formation, because that is what is present as nature. Whereas, if you have a compound like carbon dioxide, then you would have a heat of formation which would be carbon plus oxygen forming carbon dioxide. In the previous example which we looked at for Hess's law, the final equation which we had for C2H6, where you had 2C plus 3H2 forming C2H6, is a type of formation reaction where ethane gas is formed, assuming that all of them are existing in their native phases, which was not explicitly listed, but if we were to assume that, then that reaction would be a heat of formation reaction. How do we apply Hess's law when we have heat of formation? Heat of formation can be used to calculate heat of reaction for any reaction which involves compounds. Using Hess's law, if stoichiometric coefficient of an ith species can be given as nu I, and the heat of formation, standard heat of formation of the species can be given as delta F cap, delta H cap Fi, then the standard heat of reaction can be calculated using this equation, where standard heat of reaction is basically this. First you find the sum of the stoichiometric coefficient times heat of formation of the products and subtract the sum of the stoichiometric coefficients times heat of formation of the reactants, and you will finally get the heat of reaction. So, we will verify how this works. We will look at an example problem that will help us understand and apply this principle correctly. So, standard heat of formation for all elemental species will be 0 when you use this equation. So, look at this example problem. So, you are asked to determine the heat of reaction for combustion of liquid N-pentane, assuming water liquid is a combustion product. So, you might usually have water vapor as the combustion product. However, here they have given explicitly that water liquid is the combustion product, so that we can find the standard heat of reaction for this reaction using the standard heats of formation. So, we need to know the heats of formation for N-pentane, carbon dioxide and water liquid, and we can directly use these values and perform the calculations to identify the heat of reaction. While we do that, we will verify if Hess's law is obeyed and as we do the calculations. So, based on the equation which we were given in the last slide, you would have delta HR cap as sigma of nu I delta HFI cap minus sigma of nu I delta of HFI cap, and the first one is for the products and the second one is for the reactants. Now, this would mean that the equation would look like you have different components which are carbon dioxide and water liquid in the products. So, the stoichiometric coefficients are 5 times delta HF cap of carbon dioxide plus 6 times delta HF cap of water liquid, and on the reactant side you only have pentane, which is a compound. Oxygen is an element and we do not have to worry about that because the heat of formation for oxygen would be 0, and this would be 1 times delta HF cap of pentane. So, once we have the heat of formation for these things, we can actually calculate the heat of reaction. Now, before we perform these calculations, let us verify if the equation we had is correct. So, for that we will have to look at the Hess's law, and for applying Hess's law we first need to use the formation reactions. We need to start with the formation reactions. Let us see if the formation reactions will follow the same equation to get the final equation of interest. So, the formation reaction for N pentane would be 5 carbon plus 6 hydrogen gives C5H12. So, this is a simple formation reaction for N pentane. For carbon dioxide it would be C plus O2 gives CO2, and for water it would be H2 plus half O2 gives H2O. So, let us call these reactions 1, 2 and 3, and we will have to see if we can get the reaction of interest from these 3 equations and what operations we would have to do. So, the final reaction actually which is of interest actually has N pentane being combusted. So, N pentane is in your reactant side, here it is in the product side, which means minus of reaction 1 has to be taken. So, the reaction 1 has to be subtracted from the 2 and 3 reactions. Anyways, so the 2 and 3 you have again carbon dioxide as product and water as product in the reaction of interest and also in reactions 2 and 3. However, we have 5 moles of carbon and 6 moles of water being produced. Here we have only 1 mole of carbon dioxide and 1 mole of water being produced. So, we will have to multiply reaction 2 with 5 and reaction 3 with 6 to get the same number of moles of water and carbon dioxide as in the reaction of interest. So, let us do that. What we would have would be 5 times reaction 2 plus 6 times reaction 3 minus reaction 1 should give us reaction 4. So, let us see what that would be. It would be 5 C plus 5 O2 gives 5 CO2, and this next equation would be 6 H2 plus 6 times half O2, this 3 O2 gives 6 H2O, and the last equation, because we are going to subtract it, we will change the reactants on the product sides. So, that would become C5H12 becomes 5C plus 6H2. So, this is H12. Okay. Now, let us find the summation of these 3 reactions. So, this is basically 5 times 2 that I have done, 6 times 3 that I have done, and minus 1 times 1 that I have done. Adding all this, what we end up with is 5 carbon gets cancelled, 6 hydrogen gets cancelled, and you have C5H12 plus 8 oxygen gives 5 CO2 plus 6 H2O. So, using Hess's law, what you have is 5 times the heat of reaction for reaction 1, which would be reaction 2, which would be the heat of formation of carbon dioxide, plus 6 times the heat of formation for water liquid, minus the heat of formation for N-pentane, which is exactly what we did based on the equation that was given. So, if we were given the heat of formation for carbon dioxide, water and N-pentane, we can calculate the heat of reaction for the reaction of interest. So, knowing the heat of formation for carbon dioxide and water, we will plug them here. This can be obtained from your textbook or from any reference book. This would be 5 times minus 393.5 plus 6 times minus 285.84 minus of minus 173, and this value is delta HR cap is equal to minus 3509 kilojoules per mole. So, this is the heat of reaction for the combustion reaction where N-pentane liquid is burnt to produce carbon dioxide and water liquid. So, with this we have seen how we can use heat of formation for performing calculations using Hess's law and identifying the heat of reaction for any given reaction. Similar to heat of formation, there is also another type of reaction which is commonly used, which is the combustion reaction. Heat of combustion also needs to be looked at carefully. The standard heat of combustion of a substance is the heat of combustion of that substance with oxygen to yield specified products with both reactants and products at 25 degrees Celsius and 1 atmosphere. Okay. This is the standard heat of combustion. So, basically any component which you have, when it is burnt, will produce the combustion products. We have already looked at what is combustion and what complete combustion stands for when we discuss combustion reactions as part of material balances. Please go and look it up and refer back to understand what it is. And when it yields these specific products and assuming the products and the reactants are at the same temperature, the change in enthalpy for this process, for this reaction, is called as the standard heat of combustion. The standard heat of combustion can again be obtained from textbooks and handbooks, and the values in table B1 in your textbook Felder-Russo is based on the following assumptions: all carbon forms carbon dioxide, which means the reaction goes to completion, and all hydrogen forms water liquid, and all sulfur forms sulfur dioxide gas, and all nitrogen just remains as nitrogen. So, based on this assumption, the heat of combustions have been listed in table B1. So, just like how we did heat of formation and used Hess's law to calculate heat of reaction, we can use heat of combustion to calculate heat of reactions for reactions that involve only combustible substances and combustion products. So, you can create a hypothetical path where all combustible reactants are burnt with oxygen at 25 degrees Celsius, carbon dioxide and hydrogen combine to form the reaction products plus oxygen, the reverse of combustion reactions of the reaction products, and therefore, using this assumption we can calculate the heat of reaction as first the summation of the stoichiometric coefficient times heat of combustion for the reactants minus the summation of the heat of the stoichiometric coefficients and the heat of combustion of the products. If any of the reactants or products are actually combustion products, then you would use the heat of combustion as 0 for those things. For example, if you have carbon dioxide as part of the reaction, then you would have the heat of combustion for carbon dioxide as 0. So, the principal application of this equation is to determine the heat of formation for combustible substances, for which you cannot actually get the formation reactions occurring. So, the example would be the example we used for Hess's law, where we tried to calculate the heat of formation for ethane, which is C2H6, and all we did was we had 3 different combustion reactions which we combined to get the reaction of interest. So, consider the formation of the reaction for pentane, which is shown here, 5 carbon plus 6 hydrogen giving C5H12. This reaction cannot be carried out in the lab, it will not happen, but carbon, hydrogen and pentane can all be burnt to find the heat of combustion. So, then you can use these heat of combustions to get the heat of formation for N-pentane. So, this is how Hess's law is applied for using heat of combustion to get the heat of formation or heat of reactions. So, here is one example problem where we have to calculate the heat of reaction for a dehydrogenation reaction. Ethane becomes ethylene and hydrogen, and for the heat of reaction for this has to be calculated using the heat of combustion for ethane, ethylene and hydrogen. So, combustion reactions can actually be used here. So, let us see how it would be done. So, we can use the equation directly and we will also verify if it obeys Hess's law. So, if we use the equation directly, the heat of reaction would be equal to sigma of reactants nu I delta H cap Ci minus sigma of products nu I delta of H cap Ci. So, this would be the heat of reaction. So, we have reactants minus products. So, reactants would be 1 times C2H6. So, that is heat of combustion for C2H6 minus heat of combustion for C2H4 minus heat of combustion for hydrogen. Now, let us look at the combustion reaction for the individual components and try to see if these values the equation can be derived. So, you have C2H6 plus oxygen forming CO2 plus H2O. So, you would have 2 CO2 and 3 H2O being formed, involve 3.5 moles of oxygen reacting. So, that you have 7 atoms, 4 plus 3 7 atoms of oxygen, and you have C2H4 plus oxygen forming 2 CO2 plus 2 H2O being formed. So, 4 plus 2 6. So, you will have 3 molecules of oxygen reacting for this, and finally, you would have hydrogen plus half O2 reacting to form H2O. So, now let us call these as equations 1, 2 and 3. So, to get this final equation, we have C2H6 in the reactor side, reactant side. So, you can have the reaction 1 as such. The second equation, we have the reactant C2H4 in the product side. So, we will multiply this by minus 1, and the other one we will again multiply it by minus 1, so that the hydrogen goes to the next side. So, what you would have is equation 1 times 1, equation 2 times minus 1 and equation 3 times minus 1 as the operations, so that we get the combustion equations as C2H6 plus 3.5 O2 gives 2 CO2 plus 3 H2O, and the next equation would be 2 CO2 plus 2 H2O gives C2H4 plus 3 O2. So, this is basically the reverse of the second reaction which we had, and similarly the reverse of the other reaction would be H2O gives H2 plus half O2. So, now in this equation the 3, when we add these equations, the 3.5 oxygen in the reactant side will get cancelled with the 3.5 oxygens in the product side, carbon dioxide gets cancelled, water gets cancelled. So, leaving out C2H6 gives C2H4 plus H2. So, the operation we did was 1 times reaction 1 minus 1 times reaction 2 minus 1 times reaction 3, which means your delta HR cap would be equal to delta heat of combustion for C2H6 minus heat of combustion for C2H4 minus heat of combustion for hydrogen. So, this is the same as the equation which we have here, which was obtained from the equation that was given earlier. So, therefore, we can calculate the heat of reaction using the heat of combustions that can be obtained from any table. So, the heat of combustions for these values are minus 1559.9 for C2H6, minus of minus 1411 for C2H4, and minus of minus 258.84 for hydrogen, giving the heat of reaction for the reaction of interest as 136.9 kilojoules per mole. So, this is how we can apply Hess's law for combustion reactions. With this, we have looked at all the fundamentals that are required for performing energy balances in reactive processes. So, in the next lecture, we will perform more calculations to strengthen our fundamentals by performing a tutorial session on these concepts. Until then, thank you and goodbye.